Hello again, and welcome back to another video in our Introduction to Disease Modeling. This time I'm going to talk about sensitivity and scenario analysis. And this is basically our kind of what if section. First thing we have to understand with sensitivity and scenario analysis is that your model contains assumptions. If it didn't, it wouldn't be a model. All models contain assumptions. Sensitivity and scenario analysis are ways of asking what would happen if those assumptions were wrong, or slightly wrong, or maybe completely out of line. So what we're going to look at is different ways of testing your assumptions within a model. Now, just caveat up front, if I am ever reviewing your disease modeling paper and you left out sensitivity analysis, I will recommend that it is rejected. You should never, ever put a model out there until you have done a sensitivity analysis. It's essential because your model has assumptions and they might be wrong, and we need to know that. So there's two types of sensitivity analysis. There's local sensitivity analysis and global sensitivity analysis. Local sensitivity analysis says you've got one parameter, and you want to know, well, it could be a number of things. If you've just seen the model fitting videos where we end up with these distributions for a parameter, you know that there's a distribution. How much would it change your model outcomes if you varied this parameter across this distribution? Global sensitivity analysis says, yeah, but you have more than one parameter. And you kind of want to see how they all can relate to the eventual outcome across the range of their distributions simultaneously. You know, you can do local sensitivity analysis on every parameter one after another, but by doing global, you can say which parameters are driving the model most and which are, you know, this doesn't really make much of a difference in the grand scheme of things. So local sensitivity analysis. We're going to, again, work with our SIR model. And let's say we have beta, which we don't know what beta is. You know, we've fit beta before in our model fitting videos, but let's say we don't know exactly what it is, but we know it's somewhere between 0.5 and 4.5. Pretty broad range. Could be anywhere in there. Now we can run the model with beta at different values and see what the outcomes look like. So if you run it with beta of 0.5, you end up with almost no infection. Not much infection at all. If you move beta up to 1.5, you end up with this little curve, tiny little outbreak. Okay, up to 2.5, oh, this is an outbreak. Okay, we see it. Up to 3.5, we're seeing a bigger outbreak. And it's a little faster, and the distribution time is a little tighter. Up to 4.5, it's even higher. Okay, so by changing beta from 0.5 up to 4.5, we can end up with this wide range of outputs. Now, for sensitivity analysis, you can, if you want, make a graph at all of these different values. But it's really hard to actually come up with an analysis of all of these different timelines. So what we generally do is we come up with an output that we are going to look at how it changes over the course of the infection or over the course of changing this beta. Now, for this purpose here, I'm going to say my outcome of interest is the total amount of infection over the course of the outbreak. So what I'm doing is I'm taking the area under the curve of that infection curve. That's going to tell us how many people got infected over the course of the outbreak. You can choose different things. I've run sensitivity analyses on how many people die, on how many times we had to test. There's all sorts of things that you can run sensitivity analysis on. What you're running the sensitivity analysis on is the outcome that is of interest that you're worried about. Well, if I change my assumption, this outcome will change. So looking at this value of total number of infections, if we vary beta along that line from 0.5 all the way up to 5, we can see this curve that comes out for values of beta. If you're below about 0.75, you don't get much of an outbreak. In a population of 100 people, you're getting fewer than 10 infections. Very small outbreak. So we're going to call about 0.75 as this threshold value. Below that, we're really not worried. So any beta below 0.75 in this system, we're going to say, you know what? That's not really an issue. It's going to die out. Above 0.75, we get this very steep curve going up to leveling off somewhere between 3 and 3.5. We hit this almost saturation point. At this point, everybody in the population is pretty much getting infected, according to our model. And so if beta is greater than that, as far as total infections go, doesn't matter. Now, total infections is not the only possible outcome. We could say the timing of the peak is our variable of interest. And if you get above 3.5, the timing of the peak is still going to shift, but we're still going to get about the same number of infection. So we can see with the local sensitivity analysis that gives you an idea of, okay, where I get the most variability, where I see the highest change. If I'm beta below this value, I don't care. If I'm above this value, everybody's getting infected, so it's serious. It gives you all of these ideas of how much changing beta can change the outcome for this particular outcome. Now, global sensitivity analysis says, yeah, but it's not just beta, we also have gamma. So we have this beta value. We're going to now only look at beta between 0.75 and 3 because our local sensitivity analysis said, well, outside of those values, it doesn't really matter. But we also have gamma. And let's say we want to look at gamma between 0.5 and 1.5. So a gamma of 0.5 means recovery in about 2 days. A gamma of 1.5 is going to be a really fast recovery within a day. And we're going to look at those values, and we've got all of the beta values. Now, the most common way that we do global sensitivity analysis is using Latin Hypercube sampling. And just basic overview for those who aren't familiar with Latin Hypercube sampling. We have this distribution of beta between 0.75 and 3, and a distribution of gamma between 0.5 and 1.5. We're going to call them uniform distributions for simplicity. So let's say we have a uniform distribution for each. We're going to say, and for this very toy example, I've divided each of those distributions into 5 sections, 5 equal probability sections. And I'm going to draw a value from each of those sections. In this case, I've kind of drawn the value that's equidistant, but in actuality, you would take this segment that goes from 0.75 to maybe 1, and you would randomly draw a value in there. So we have a value for each of these 5 equidistant sections. And then we're going to randomize the order for beta. And then we're going to randomize the order for gamma. And so now we have random draws of beta, but making sure that we've covered the full range of the distribution, and random draws for gamma, again, covering the full range, but they're randomized in order to each other so that we have a coverage of the full potential state space, but efficiently. And that's basically what Latin Hypercube sampling does. It gives you an efficient coverage of the full possible state space. And then all we do is we simulate. So I take a beta of 3 and a gamma of 0.75, and I stick it into my SIR model, and I say, how many infections am I going to get over the course? And the model says 131. Okay, what if beta is 1.9 and gamma is 0.5? You're going to get 195. So we go through each of those values. Now, this is a toy example with only 5 draws. Generally, you do more than that. But if we do this toy example where we have 5 different sections to our distribution, we can run it through, get our results, and then we can look at the correlation between beta and the total infections and between gamma and total infections. And if we plot these 5 points and fit those lines here, you can see that beta has a direct relationship. Increase the transmission coefficient, you get more infections. Surprise. Yeah, it's clear, but you can actually estimate that correlation between those values. Gamma has an inverse relationship. That's because as you increase gamma, you decrease the length of the infectious period. Because remember, the length of the infectious period is 1 over gamma. So we're seeing an inverse relationship between gamma and the total number of infections, a positive direct relationship between beta and the total number of infections, and we can calculate a correlation coefficient. And what we generally will do is calculate the Pearson correlation coefficient for each of those values. So again, we have this graph here, and if we run it with more than 5 points, so say 100, we can actually calculate these Pearson correlation coefficients. Gamma is about -15, beta is about 11. And we can calculate the p-value around those if you want a p-value. Obviously, with just 2 parameters, making this tornado graph, which is what this graph is called, it's not much of a tornado, and they're both very important. But if you have a bigger model with a lot of different parameters, you'll have a lot of different values. Some of them will probably be non-significant. Others will be highly significant. So which ones pop up as highly significant in your global sensitivity analysis? Those are the parameters that are really driving your model results for the result that you are measuring. Remember that you can end up with different possible results to measure, and you can end up with different correlation coefficients with those different results. So this is for the result that you are measuring. These are the important variables. What does that mean for you as a modeler? You can look at those and say, okay, here, gamma is clearly really important over this potential range of values. The gamma makes a difference. I want to make sure that I have measured gamma as best as I can. Gamma is the important one to make sure that my fit is good, that I have the true value. So that's sensitivity analysis. Scenario analysis is a slightly different what if. It's saying, I want specific scenarios. Now the scenario might be, what if my model is slightly different? What if instead of an SIR model, I have an SEIR model? Or it could be something fairly simple, like, for example, in this, what if half the population was immune at the beginning of the outbreak? So here on the left-hand side, we have our outbreak from before, showing our normal SIR curve. And on the right-hand side, we have the outbreak. If we start with 50 out of 100 people are already in the removed category, meaning they're resistant, they've already had the infection, they're immune. And you can see that it changes the values a lot. So these scenario analysis can be used to ask very specific questions. You can ask a question like, well, what if I moved to a population with a different age structure? Or what if I used a different population size? All of these are scenario analyses that ask very specifically, what would my model do if I changed how I applied it? And scenario analyses are important to test those bigger assumptions that you're making. When you build your model, you make certain assumptions about your population, about your model structure, about everything that you're putting in at the starting point. And this is a way to check those assumptions. So big takeaways to remember about sensitivity and scenario analysis. You need to outline your model assumptions. Your model makes assumptions. Put them down on paper, list them out, then test the importance of those model assumptions. And that's where you use sensitivity analysis for the assumptions about parameter distributions and parameter values, and scenario analysis for assumptions about model structure, population structure, population that you're applying it to. And use those tools, sensitivity and scenario analysis, to identify assumptions that could drive model results. Sometimes you'll find an assumption that you made that could be a deal breaker. That this is an assumption that I'm choosing to make, and if I'm wrong, everything changes about my model output. When you find that, that's when you start to use those scenario analysis, sensitivity analysis to say, okay, here's where my model could break. Am I concerned that my model is wrong enough to not be usable in this scenario? What data do I need to gather to make sure that my assumption is not a deal breaker? So sensitivity and scenario analysis, this is why I say if you send me a paper that has a model that you did not do sensitivity analysis, I will reject it, because this is what tells you whether or not your model can be used as is, or if it's identified holes that you need to plug in your knowledge, in the literature. These are just essential to modeling. You have made assumptions. Now you have to test them. All right, see you again very soon.